So welcome everyone. Today we're going to have Ms. Leslie Wessels talking about near vector spaces. Excited to see what this is about.
Okay, I didn't hear you so well, but I'm assuming I can start now.
Yeah, sure.
Okay, so I am a PhD student about to submit my thesis for examination. But instead of talking about what my thesis was about, which is I think a bit too complex for first or second year students, assuming that there are first and second year students in the talk. So I thought about just doing a brief introduction to what near vector spaces is or are. The overview of the talk is basically I need to define what a field is. So hence the question, what is ZP? Because near vector spaces can be defined over set of endomorphisms, but you can also define it over fields. So that's what I'm going to do, and specifically ZP. And then I'm just going to do some examples of isomorphisms because hopefully I can explain to you or at least show you the definition of a near vector space, because I'm not starting with that because it can seem complex. So for that you need to know what an endomorphism and an automorphism is. So we'll do some examples of isomorphisms, and then at least I would like to do a vector space opposed to a near vector space over ZP. And then the references that I used is a book by Fraley and also by Hill. So yeah, first course in abstract algebra and a first course in coding theory. So and also if there are any issues, can you just let me know? And then also for those who know near vector spaces, I'm used to working with scalars on the right-hand side. So for this talk, I'm going to work with scalars on the left-hand side. So if I make that mistake, can you please stop me and rectify me? So, okay, so the first question is, what is ZP? So some of you will probably know what ZP is and also be familiar with us using P to denote a prime number. So let's start with Z3. So Z3 is the set of where you have elements 0, 1, and 2. And let's consider two binary operations, plus and multiplication. So I'm basically going to define what a field is, but I'm just going to go through this systematically and using this example. So if you look at the tables, the addition table and the multiplication table, you'll see that the elements have certain properties. For example, the first case, if I look at the positive or the addition table, I have that if I add any two elements, I'm going to get an element back in Z3. So in other words, we have for all A, B in Z3, I have that A plus B is back in Z3. And exactly the same for the multiplication, but in this case, okay, so for all A, B in Z3, I have that A times B is back in Z3. Also, you'll note for the multiplication, normally we only work with the non-zero elements, because it's very trivial that if you, well, we work with the non-zero elements because eventually we want to work with, we want to get to inverses. So I'm just going to write down what's on the left-hand side for addition, but it's exactly the same for multiplication because it might take a bit of time. Then also, the second property, you'll see that there exists an element so that if I add any other element in Z3 to that element, I get my original element back. In other words, there exists, let's call it an identity element in Z3 such that for all A in Z3, we have that A plus, sorry, I called it the identity, is equal to A again. And the same for addition. Then the third property, I have that if I add certain two elements together, I get that identity element. In other words, for all A in Z3, there exists A minus A in Z3 such that, or ZP, I'm just using Z3, such that A plus minus A gives me that identity. And remember, this is just my zero element. And then, well, this isn't so clear to see from the table, but for all A, B, and C in ZP or in Z3, we have that A, plus B plus C is equal to A plus B plus C. So this is my associative law. This is, we have inverses, and this is, we have an identity element. And then if you have all of those properties, we will call Z3 a group in this case, under addition and multiplication. So in that case, we have Z3, we write Z3 under addition, but then Z3, and I'm going to use a star because that star means I am taking Z3 without the zero element. Under multiplication is a group. Okay, so groups with the added property, the following. So you'll also see that it doesn't matter if I add A and B, it doesn't matter if I write A in front or B in front, I will get the same element. So for all A, an element of Z3, we have that A plus B is going to be equal to B plus A. Exactly the same for multiplication. And with that particular property, we call that commutativity. We have that Z3 is an abelian group under, I shouldn't write it like this because with multiplication, Z3 should be without, with multiplication, it should be without the zero element. And Z3 under addition is then an abelian group. Okay, so now that is what a group is. Now we need to get to what a field is. So with a field, I need an additional property, which is, we say that multiplication distributes over addition. So for all A, B, and C, in Z3 we have that A times B plus C will be equal to AB plus AC. Okay, so for a field, we have that we look at our structure with both binary operations. So in this case, our Z3 would then be what we call a field. So we want that Z3 under addition must be abelian. The non-zero elements must be abelian under multiplication. And then we want the following, distributivity. But you'll notice that I didn't write the right-hand side because you actually, in some books, they just write it in this way. They just give you the left distributive law. But remember, I can, because my non-zero elements are commutative, I can also write C times A, which means this is going to be equal to B plus C times A. So I basically, you do have both distributive laws. So if you think about it, we are doing near vector spaces. So you also get a near field. So with near structures, it's generally when one of the distributive laws are missing. So with near fields, one of these distributive laws will not be satisfied. You will only have one of them. And you'll see how near vector spaces will be different to vector spaces, but it has to do with the distributive law. Okay, so we have that Z3 is a field. So normally we want an identity element for a multiplicative and also an additive identity element. And then that means we always want inverse elements, whether it's under addition or multiplication. So think about why Z6 will not be a field. And then also Z4 is not a field. So why would that be? So if I look at the table, the multiplicative table for Z4, you'll see that first of all, if I multiply 2 to itself, I get 0. And if you look at the previous tables, you'll see that you kind of have a Sudoku effect. Like within a row or within a column, you don't have a repeat of a particular element. So an element only occurs once in a row or in a column, and this is not the case for Z4. And then also you can see that 2 does not have an inverse element. But we can find a field of order 4. So I'm not going to go into detail regarding this, but generally we use the notation GF2, and this is basically exactly our set Z2. And we can define an extension on this particular field because we know that GF2 is definitely going to be a field, which is 2 to the power 2, which is 4. And you can actually set up a table and elements where the only constants is going to be 0 and 1, where you have that GF4 will then be a field. But like I said, I'm not going to go into detail here. So this is named after a French mathematician. I would suggest that you read up on him. He actually has quite an interesting story. He developed this theory before he was 22 or 23, and that's when he unfortunately died. So he was quite young to develop this theory, also to die. But yeah, I could say more about that theory and all of the applications of that theory, but I'm worried about the time, so we can always come back to that. Okay, so next, what we need to define is what an automorphism and an endomorphism is. So let's just look at these two binary algebraic structures. So what is a binary algebraic structure? It's basically a set with a binary operation, such as S and star and S prime and S star. So if I look at the elements and the tables regarding these binary operations, you'll see that they actually look similar. Maybe it's not that obvious, but okay, so sometimes structures, they are so similar that you can actually define a mapping from one to the other. So in this case, let's let our mapping be F, and I actually want to show that they are similar. So let's say if I look at my tables, so if I look at this minor diagonal, I'll think, well, maybe let's map C to beta. So F of C goes to beta, and then let's say B goes to alpha, and then A goes to lambda. So now the thing is, when you have an isomorphism, or one structure is isomorphic to another, you want how the binary operation acts on the one set, you want it to be preserved in how the second binary operation it acts on the second set. So in other words, if I say, well, what is A star B? So I look at, so let's say my first element is in my row. So A star B will give me B. So what I would like is for F of A star B, because remember now A and B are in S, so it's just star, should be equal to F of B. Okay, so let's see if that is the case. So on the left hand side, F of A star B is yeah, so this is going to be F, sorry, this should be F of A star prime F of B. This is what I would like to happen. So let's see if we actually get that. So on the left hand side, I have F of A star B is then F of B. So what is F of B? So F of B, I said, should be alpha. Okay, so let's look at this is my left hand side. So my right hand side is F of A star prime F of B. So what is f of A? F of A is lambda star prime. What is f of B? I chose f of B to be alpha. So what is lambda star prime times alpha? That is beta. And these two are not equal to one another. So this mapping is not going to work. Sorry. So let's see if this particular mapping works. So A, let's choose another one, B star C is equal to, so B star C is equal to A. So what is f of B star C? So that should be f of A. So what is f of A in this case? It's equal to beta. Okay, so that's my left-hand side. So my right-hand side is f of B star prime f of C. So what is f of B in this case? It's alpha star prime. F of C is lambda. So alpha star prime of is equal to beta. So this mapping, where map A to beta, B to alpha, and C to lambda, satisfies, or at least it preserves, the multiplication. So now we get to, so I hope you more or less have an idea of what we mean by isomorphic. So, and also you'll note that we have the same number of elements and basically the same structural properties. So what is the definition of isomorphism? So we have two binary algebraic structures, or S star and S prime star prime. And isomorphism of S with S prime is, first of all, and I will discuss this, a one-to-one function, phi. It's a mapping. This is also something we're going to discuss, S onto S prime, such that the following property is met. And this we call a homomorphism. Okay, so this, the homomorphism along with a one-to-one and onto mapping is called an isomorphism. So let's discuss how to show that one binary structure is isomorphic to another. So the first thing that you will do is you'll define a function that gives an isomorphism. So, and then the second step is we want to show that phi is one-to-one. So this we also call injectivity. Okay, so in school I suppose we had two sets. So if you think of a normal function, we have that two elements in set A can be mapped to one element in B. But for one-to-one, a one-to-one mapping, I don't want this particular situation. So how do I show that something is one-to-one? I show that if I have that the image, let's say this is X and Y, that the image of X and Y are the same, then I need to show that X must be equal to Y. They can't be two separate elements. So that is one-to-one or injective. And then onto is what we call surjective. So what is onto? It means that every element in B, there must be a pre-image for that element. So for all elements, for all Y in B, there exists an X in A such that my function will map X to that particular Y. So in other words, all the elements in B must be used up, or it must have a pre-image. And then also for one-to-oneness, you can only have one element in X going to an element in B. And then the last step is you want the homomorphic property to be true. Okay, so I've written down 3 examples. I'm probably not going to do all 3 of them. I see it's half past. So I'll leave the first one as an exercise. So let's do the second one. But before that, let's just answer these questions. Are those two, the integers and 2 times, or the even integers, even numbers, under addition, are they isomorphic? And you might think that because the even numbers are contained in the integers that they aren't, but this answer is actually yes, they are. And you can use those steps to prove it. You just have to find a function that you can use to show that they are isomorphic. And then, so this might look strange. I have the real numbers under addition and the positive real numbers under multiplication. Would they be isomorphic? And the answer here is yes again. And then number 3, so I have the integers under multiplication and the positive integers under multiplication. Would they be isomorphic? The answer here is no. So let's do number 2, because I think number 2 is interesting enough, because it's one set is under addition and the other is under multiplication. So what's our first step? Our first step is to define a function. So we define, let's use this is B. So number 1, let's define phi from R to the additive, or the positive real numbers. Okay, so to get an idea of what we will, if I take an X in my set A, what I would map it to. So remember, in this case, we want the homomorphic property to be true. So what function do you think will have the following property? Because now I'm working under addition. So if X and Y is in the real numbers, this should then be equal to phi of X times phi of Y. Okay, so what function do you think, or do you remember, as that property? And that would be any exponential function. So we could choose X to go to e to the X. So in other words, phi takes X to e to the X. So the second step is we want to show that this is injective. So we'll suppose, and this is normally how you show that a mapping is injective. So suppose f of x, so x, y, z, r, and suppose that f of x is equal to f of y. Sorry, not f, phi. But what is phi of x? In this case, we said it's e to the x, and phi of y is e to the y, and we can just take ln on either side, so we have x is equal to y. So that means phi is 1 to 1. Then our third step, so in this case, how do we show that something is injective? So we want to show that for all, let's say y in, so this is going to be r positive real number. So suppose, for all y in r plus, there exists an x in r such that phi of x is equal to y. Okay, so we'll start with y. So let y be a positive real number. Then you know that for positive real number, we can take ln of y, and then ln of y will then be in the real numbers. So it's negative and positive. So we can then say, well, let's take x to be equal to ln of y. Then phi of x is phi of ln of y, which is e to the ln of y, which is equal to y. Okay. And then the fourth step is we need to show that phi of x plus y is equal to phi of x times phi of y. And you know, of course, that this is true. So, for x and y in R, phi of x plus y is e to the x plus y. And remember, we can write this as follows, which means this is phi of x times phi of y. And we have shown that there is an isomorphism, or the two structures are isomorphic. Okay, so that is what an isomorphism is. So you have injectivity, surjectivity, and you have the homomorphic property. So what is an endomorphism? So an endomorphism is basically you have a homomorphism or homomorphism from a structure to itself. So you just have the one property, the homomorphic property. And then automorphism is, so this is a homomorphism from a structure to itself, and an automorphism is an isomorphism. So now you want not just the homomorphic property, but injectivity and surjectivity as well. So isomorphism from a structure to itself. Okay, so that's what an endomorphism and an automorphism is. So now we get to a vector space over ZP. And like I said, you don't need to, near vector spaces aren't just defined over ZP. So, but I'm just concentrating on this particular structure. So let's look at the difference between a vector space and a near vector space in terms of Z3. So let's say we take 3 copies of Z3. So let's define VS as my vector space. And these are possible elements, 2, 0, 1 and 1, 1, 2. If I can just use that as an example. And then I'm not sure how familiar you are with vector spaces, but I'm not going to go into too much detail. What I will do is just concentrate on that property where the two differ. So just to define the two operations on a vector space, I have addition. So I can, if I have x and y of vectors, I can add them, and that's the same as just adding their components. Just to remind you, normally vector spaces in R2 and R3, in 2 dimensions or in 3 dimensions, that gives you the number of components you have. And with R, you can, the components or elements or are real numbers. In this case, you have a restriction because we are working with elements in Z3. So my elements can only be 0, 1, and 2. Okay, I should have probably taken Z5, but it doesn't matter. So in this case, if I add 2, 0, and 1, and 1, 1, and 2, this will be 3, so that is going to be 0, that's going to be 1, and again that's going to be 1 plus 2, which is 0 in Z3. And we have scalar multiplication for A in Z3. So let's say A is 2, and I'm multiplying it to 2, 0, and 1. I get 4, but in Z3 that's going to be 1, 0, and 2. Okay, so normally when you do structures, you always want to see, well, those properties that we did in the beginning, commutativity, if I add 2 vectors, doesn't matter which one I write in front, all those properties, I'm not really going to go through those again. I feel like you guys will be, that is understandable for you guys. So the property that I want to concentrate on is the following. So I'm multiplying on the left-hand side. So if I have A and B in Z3, 2 scalars, let's say 1 and 2, and I multiply it, so 1 plus 2, so basically I'm looking at A plus B times X. Let's say that is X and that is Y. So this is exactly going to be A times X plus B, times X. Because on the left-hand side, I have A plus B times X. So let's say that is 1 plus, okay, let's make it both, let's make both 2, otherwise I'm just going to multiply by 0. So let's say I'm taking 2 times 2 times 2, 0, and 1. So 2 plus 2 in Z3 is equal to 1. So I'm just multiplying 1, 2, 0, 1, and 2. I get the same answer. On the right-hand side, going to get the same value. So I have A times X plus B times X. So I'm going to get 2 times 2, 0, 1 plus 2 times 2, 0, 1. This is going to give me 4, which is 1, 0, and 2. And this is going to give me again 1, 0, 2. If I add them together, I get 2, 0, and 4 is going to be 1. Okay, so for vector spaces, that is true. That is the main difference between vector spaces and near vector spaces. But let's first look at how we define a vector space, or not the definition, in terms of an example. So I have a scalar, well, consider VA, where V is, well, it's a copy of A, and let's say A is the field Z5. So we define a scalar multiplication for all x1, x2, and x3 in V and alpha in A as follows. So you'll see that it's not a straightforward multiplication because my alphas, certain alphas are raised to the power 3. So that's because when we let alpha act on, let's call this x, it's actually a multiplicative automorphism. So phi 1 of alpha times x1, phi 2 of alpha times x2, and phi 3 of alpha times x3. So in this case, phi 1 and, well, sorry, psi 1 and psi 3 are the same. I'm raising it to the power 3, and my psi 2 is the identity automorphism. So you'll probably wonder why particularly 3, and I'll probably answer that after I've given the definition of a vector space, if I have time. So just to illustrate that this particular property over here is not met. So let's say, what example did I use? So we are in Z5. So let's say I take 2 and 1 in Z5, and let's say that is alpha and beta. So alpha plus beta times x1, x2, x3. So this is going to give me, in terms of 2 plus 3, 2 plus 1. So multiplying 3 to, let's say we take, let's say 2, 0, and 1 in V. So I have 2, 0, and 1. So now remember, if I multiply the scalar for the first and the last component, this is going to be 3 to the power 3. So I'm multiplying 27 actually to 2. That's just going to be 0. And I'm going to get 27. So modulo 5, or in Z5, this 27 is just going to be 2. So 2 times 2 gives me 4. And that is just going to be 2. Okay, so that is my left-hand side. So I'm going to show that this is not equal to alpha times x1, x2, x3 plus beta times x1, x2, x3. So I have 2 times 201 plus 1 times 201. So if I take that 2 in, it's going to be 2 to the power 3. It's 8 times 2. That's just going to be 0. And that's going to be 8. So you can already see in modulo 5, in Z5, this is going to be 3. 3 times 2 is 6, which is 1. And 8 is just 3 in Z6, in Z5. So I don't have this distributive law for near vector spaces. Do I still have time, or maybe I can, people can ask questions about anything else that they're wondering about, because I think it's 10 to already.
Yeah, sure. So
maybe I should just put up the definition that Andre, and you'll see why I didn't start with this definition, because I have 5 conditions that need to be met, and then you have something called the quasi-kernel. Yeah, so let me just stop here, and then maybe if anyone has questions.
Sure. Cool. So the floor is now open for any questions.
Yes, I do have a question.
Is it Gregor?
Yes, hello.
Hi.
So in point 4, you gave this example for a near vector space. So that means that not all the properties of a vector space are met. So does that mean like only one property is not met, but all the others have to be like still valid? Or...
I think the others are still valid. This is the main difference.
Okay. But so my question is like to be a near vector space, is there like any number of properties that
yeah, it's these. So I actually wanted to get to this, because that's why I said what an endomorphism is, what an automorphism is, because for VA to be or V to be a near vector space over A, I need certain properties for V, and then also certain properties for A. And also you'll see my scalars are on the wrong side of what I just did with you guys. It's on the right hand side, which previously I did everything on the left hand side, all the scalars on the left hand side. But yeah, maybe some other time I can go through these properties. I don't know how understandable it's going to be for you guys with, I mean, you in second year now. So
I guess we can have a follow sometime.
I could follow you with most of the things, I think.
Yeah, it's difficult because I really had to go back to the actual basics of abstract algebra, and then I couldn't get to the real in-depth ones, especially when it comes to how you choose these. Yeah,
Yeah, that's a very interesting thing to understand in more depth. But yeah, thank you very much for the detailed explanation so far.
Pleasure.
Hi, Leslie.
Hi.
Hi, I just wanted to quickly ask, I was only able to join a little bit later. So do you possibly have, yes, it's me. Hi. I just wanted to find out, do you possibly have any extra reading on this topic that you could maybe recommend if we wanted to learn a little bit more?
About the finite fields?
Yeah.
Specifically?
Yeah.
Well, I think this is a good book. A first course in
right.
abstract algebra by Fraley. And then also, I said about Galois theory. Coding theory is actually an application, because error correction codes are based on finite fields.
Really?
And yeah,
and you that this morning.
Hey?
And we did error correction codes this morning in computer science. That's very timeless.
So did you? Well, the thing is, you do computer science, so you're working in GF2 because it's 0-1 binary code. So already you have met Galois theory.
Oh, that's so cool. Thank you.
Okay.
So you mentioned how finite fields get used, for example, in computer science. Do you know of where near fields get used or near vector spaces?
Oh, that Dr. Howell, my supervisor, is would probably be able to answer that, because I'm not really an applications person. I really, if it's obvious, yeah, but so near vector spaces, I think Dr. Howell is busy working with a physicist, and they are finding applications in or trying to find applications in physics. And then I'm not sure if there are any applications to matroid theory. I'm not sure if Dr. Howell can
Yes. Hi everyone. So I can maybe just come in there and Leslie mentioned some of the things that we are investigating. So there's so far, well, there's actually 3 projects that are looking at the application of near vector spaces. So one is with a physicist, like Leslie mentioned, and we're trying to find a way to use these nonlinear structures to model some systems in physics. So that's an ongoing project. We haven't got anything concrete yet, but we're all confident that once we find the correct setting, that this will be a very useful tool for analyzing some of the systems in physics, nonlinear systems that have been difficult to capture up to now by using linear systems. So that's the one thing. Secondly, I think Jacques is also here. Jacques is involved in a project where we are actually looking at Andre's original papers. So Andre is the person who defined the near vector spaces that Leslie spoke of today. And he originally did a lot of work in geometry. And we have recently found some papers that are written in English. Most of Andre's papers were written in German. But Jacques found some papers that are written in English, and they've been very insightful in understanding what his idea was when he defined these structures. And I'm happy to report that there are definitely applications of near vector spaces in geometry. We are still learning exactly what it means and why they are useful, but hopefully in the future, Jacques will be able to tell you more about that. And then thirdly, I'm also involved in a project where we are looking at near vector spaces from a matroid theory perspective. Matroid theory is a way of studying linear dependence and independence but in a more general way than what we're traditionally used to, say, for vector spaces. And that's something that I'm hoping to chat to you about next week, or at least just give you an introduction of Mayport theory. So I'm working with a professor in America on studying the Mayport theory of near vector spaces. And so far, they've already given us some very interesting examples that Mayport theory hasn't seen before as a result of this nonlinear behavior. I also am aware that there are applications, possible applications in computer science from an automata theory perspective. It's something I discussed with Jaco Geldenhuys, but as you may know, he's recently resigned. It's a project that we started, unfortunately, as a result of all the changes and also of him leaving now. The project didn't get as far as we had hoped. But we are confident that there's something there that we can say about near vector spaces in an automata theory setting. And for specific automata, it may give us some interesting properties that we wouldn't have had necessarily with just a vector space structure. So I hope that answers your question.
Thank you.
I just wanted to mention, I also have a very nice application of near vector spaces to a finite linear game. For those of you, I don't know if we did this every year, but I know in the past 3 years we did do it. We discussed finite linear games as part of our first year linear algebra course, where there's this very nice example in pool that if you press switches in a certain order, you can manipulate which lights in a circuit are on. And last year I gave a sums talk where I explained what would happen if instead of a vector space structure, you used a near vector space structure. And if any of you are interested, then you could maybe let Lawrence know and I could ask him to share that talk with you and then you can have a look.
Yeah, that sounds really interesting. Thank you. Okay, so it's 2 o'clock at the moment. So if anyone has any last questions, now's the time. Okay, well, in that case.
Sorry, I didn't even thank you guys for asking me to talk. So thanks to Lawrence, thanks to you and the rest of the sums team.
No worries. Thank you for talking. I found it really interesting. I'm sure I speak for everyone on that.
Thanks.
Yeah, thanks for giving us some of your time.
Pleasure.
Anyway, well, that's it for this week. Thanks for joining, everyone. And I hope to see you next week again.